Welcome back to Algorithmic Game Theory. Last time we introduced the topic of mechanism design with money, and we also introduced the definition of a truthful mechanism. Today our goal is to better understand what necessary and sufficient properties mechanisms have to fulfill in order to be truthful. But before we come to this, let's quickly recap all the definitions. We'll have n players, or in this context we often call them bidders, and we number them by 1 through n. And we have an outcome space X. This may be in general an arbitrary set, although today we'll make a more restrictive assumption what kind of an outcome space we have, but we'll come to this. Now each player has a private valuation function which maps from the set of outcomes to real numbers, which means every player assigns a value to each possible outcome. This might also be a negative number, which means that the player associates some cost to this outcome. Good. Now we call capital VI the set of all possible valuation functions for player I. And capital V is the Cartesian product of these, so this is the set of all valuation profiles. Now, we defined this last time more generally, but for today it is enough to think about direct mechanisms. A direct mechanism now corresponds to an outcome rule and a payment rule. In an outcome rule, the outcome rule determines an outcome, and the payment rule determines the payments. Both of them take as the input a claimed valuation profile, because each of the players bids something, and in a direct mechanism, the bids are what they claim their valuation is like. And now the outcome rule takes all of these and maps it to one of the outcomes from the outcome space. And at the same time we have the payment rule, which maps on this to a payment for each of the players. For example, we were considering these single item auctions where possible outcomes were who wins the item, and then usually we made the winner pay something and the losers didn't pay anything. But in general, we are not restricted to this kind of a mechanism. Now, what are the players' utilities? The players' utilities are quasi-linear utilities. So when we're now seeing the bids, so what the bidders or the players claim their valuation is like, we now compute an outcome F. And then we evaluate the true valuation VI on that outcome. And from that we subtract the payment that the bidder is making. And the difference of this is a player's utility. Once again, we have the superscript m here, which we often leave out, which refers to which mechanism we're applying. Then we have this depends on b, which are the strategies in this game. But then this also depends on vi, the private valuation function, which we as the mechanism designer don't know. And therefore we were interested in what we call dominant strategy incentive compatible, or for short, truthful mechanisms. A mechanism, a direct mechanism, is called dominant strategy incentive compatible if this following inequality holds. What's that? Any player gets the maximum utility when they bid their true value rather than any other bid, regardless of what the other players are doing. So this is written down here. For any bid profile, it can only increase my utility if I unilaterally deviate to vi instead of bidding bi, whatever bi might be like. Okay. Today we'll get a deeper understanding of what this actually means, and we'll do this for a special case of mechanism design problems, namely single parameter problems. What are these? Our assumption today will be that our outcome space X is a subset of vectors of non-negative reals, n-dimensional vectors. And each valuation function is given as vi times xi for some vi, which is a real number. So again, we're overloading notation here, like we did this for single item auctions, where this vi, this would be the function associating a value to each outcome. And we now say, okay, this we can actually express by some real number times the xi that I'm getting. What might this look like? For example, we might have the single item auction, which we would simply represent as x being all the vectors in 0, 1 to the n, where the sum of the xi is equal to 1. Now we're getting exactly what we want, namely, okay, first of all, this is a subset of r to the n greater than 0, and here now we have xi is equal to 1 if player I gets the item, and it is 0 otherwise. But there are also other settings that we could capture. To mention just one simple example, we might have multiple identical items which we'll also define this way. But then we'll have at most k, so we might either have here equal to or at most k, and this means that we have k identical items. And each player will still only get 1, at most 1. So rather than having only a single item now, we might now have 2 identical items, but the thing is, each of the players will get only one of these, at most one of these items. We could also easily define this, and this would just mean that we would change this here to 0 up to k, so that a player can actually receive also both items. But then we are restricted in what the valuation function is like, namely that getting both items means double the value for the player compared to getting only a single item. And there's many more things that you can model this way. We'll come back also to the sponsored search auctions later today. But before we're getting there, we'll discuss our main result for today, which is a characterization of what makes mechanisms truthful mechanisms in such a single parameter setting. We'll now come to the main result of today, which is a characterization for single parameter problems, what makes mechanisms truthful mechanisms. This is called Meyerson's lemma, which is a result by Roger Meyerson from the 1980s. Why is it only a lemma? Why isn't it a theorem? Because Roger Meyerson was actually interested in something different, which will come to later in this class. For today, we'll only see what makes mechanisms truthful mechanisms. More precisely, what is our question? Our question is, for which outcome functions, so these were functions that take a valuation profile and map to an outcome, is there a payment function so we only have to assign payments to the bidders such that the combination, so the mechanism F, P is truthful. Such functions we call implementable. So this is an even more complicated question than just asking, if you give me an F and a P, is this a truthful mechanism? But we're even asking, you now give me this F, and I have to tell you whether there is a chance that you can actually build a truthful mechanism with this. Can you just give me any P such that this will be a truthful mechanism? And interestingly enough, for these single parameter settings, this is very easy to say because it is equivalent to this function f being monotone. What do we mean by monotone in this setting here? We now say that an allocation rule f for a single parameter setting is monotone if for all players and all bids for the other players, the function that maps z to f subscript I of z, b minus I is non-decreasing in Z. So what might this look like? Maybe let's see this also happening in an example. Recall the single item auction. And let's consider f as the function that assigns the item to the bidder with the highest bid. Then what will my fi of z comma b minus I look like? Well, it will look something like this. We now keep the b minus I fixed, and here I'm drawing z, and here I'm drawing fi of z comma b minus I. Then this function will be 0 for some part, and then it will be 1 for some other part. And where is this turnover point? This is exactly here as the maximum of all other bids. Because I'm not stating here how exactly what we're having exactly at this point, because this is just a matter of tie breaking, but the function will now look like this. First, I'm not getting anything while I'm keeping the other bids fixed. And so we're keeping the other bids fixed all the time. Now I just slowly increase my bid. First, I'm not getting anything, and then there's the point at which I'm becoming the bidder with the highest bid. And suddenly my outcome from getting nothing to getting the item increases from 0 to 1. This, of course, would not be true if we were, for example, considering if we're giving the item to the bidder with the second highest bid, because then suddenly I could, if I were going further, then suddenly this would go down again. And so we're calling an allocation function f monotone if it always looks like this. So increasing my bid can only give me more. For example, this might not have multiple steps if I were saying, okay, here now I'm getting 2 items, for example. This might even be a continuous function if I have divisible items. So this is far more general than just a single item setting, but for the time being, it's okay to think about it somewhat like this. What does Meyerson's lemma now state? It now says that for single parameter settings, first point would be an allocation rule is implementable if and only if it is monotone. The second point is that if f is monotone, there is a unique payment rule P such that f, p is truthful, assuming that a 0-bit implies a 0 payment. And it is given by pi of bi, b minus I is equal to bi times f I of bi, b minus I minus the integral from 0 to bi fi of t, b minus I dt. Good. So, what's our claim here? That we actually have two claims. First thing is, an allocation rule is implementable if it is monotone, and if it is not monotone, then it isn't implementable. So, this is not only necessary but also sufficient for a truthful mechanism that we have this monotonicity of the allocation function. Of course, you can still define payments such that you get such that you don't get a truthful mechanism, but you also always can find payments such that you get a truthful mechanism if your allocation function is monotone. And then it doesn't only say, okay, there are just payments, but it also says there are unique payments. There is a unique payment function, assuming that a 0-bit implies a 0 payment. And it's not only an existential proof, it is even constructive. It just gives us an exact formula how to compute these payments. Some formula that we will understand when we're going through the proof of this. So, what do we want to do next? Of course, we want to prove this. We first want to see, for example, what if an allocation rule is not monotone? Why can't it be truthful? Or if it is monotone, why can there be a truthful mechanism? Our goal is now to prove this theorem. And the first thing that we will observe is that actually for an allocation rule to be implementable, it is necessary that it is monotone. And while we're doing this, you can see how all these arguments work. And effectively, this isn't as complicated as it may sound at the very first look. So how can we now show, for example, that an implementable allocation rule has to be monotone? Let's consider any allocation function. Once again, what are the utilities? The utility, when I bid z and the other's bit b minus I, and my value is vi, then this will be, actually generally it will be vi of f of z comma b minus I minus pi of z comma b minus I. And in our case now, because we're in a single parameter setting, we say this is vi times fi of z comma b minus I. Here we are using that the problem we're considering is a single parameter problem, so the outcome space actually has the respective form that outcomes are vectors of real numbers, and vi is a function that is equal to vi times xi. Now, if f comma p is a truthful mechanism, for all y and z, we have to have my utility when bidding y against any other bids, and my value is y has to be at least as much as what I'm getting as my utility when I'm bidding z, and my value is y. So we might now write this down as y times fi of y comma b minus I minus pi of y comma b minus I. This has to be at least y times fi of z comma b minus I minus pi of z comma b minus I. This might already be a little confusing. Where do these things now come from? And I'm often mixing these up, but I think this time I'm getting it right. This y here, this is this y. So this was our vi. Our value might be vi, so vi might be equal to y, and this is then what we're getting out of this. And here, what we're getting as input to the functions, what the mechanism is working on, this will be the bids. So this is y here, and this is z here. Now, the funny thing is, if we now swap y and z, the same inequality still has to hold, because it might also be that z is the true value. So we also have that ui of z comma b minus I comma z is at least ui of y comma b minus I comma z. Or, written out, z times fi of z comma b minus I minus pi of z comma b minus I. This will be at least z times fi of y comma b minus I minus pi of y comma b minus I. What can we now observe from this? Maybe let's give these different colors so that we can distinguish these. Let's make this one red, and let's make this one blue. And let's now first talk about the red inequality. The red inequality tells us that y times fi of z comma b minus I minus fi of y comma b minus I. This is at most pi of z comma b minus I minus pi of y comma b minus I. This is all coming from the red part. And then we also have the blue part, which we can now again use to say, okay, this now has to be at most z times fi of z comma b minus I minus fi of y comma b minus I. Good. So if we now combine these inequalities, we suddenly get this kind of an inequality. And this is already interesting, because the first thing that we can observe is the following. If we ignore this middle part, which says something about the payments, it says something about just f, and how f changes when we change its input. So this is our first observation. If y is at most z, then fi of y comma b minus I will be at most fi of z comma b minus I. Why that? Because we might also just subtract this and then we would have y minus z times fi of z comma b minus I minus fi of y comma b minus I. And then this would be non-positive, so because y minus z is negative or non-positive, the other part has to be non-negative. Cool. And this is already stating that if f comma p is truthful, then we'll have to have this monotonicity. So all that is remaining now is to say, what if it is monotone? How do we then get a truthful mechanism? And moreover, why is there a unique way of setting the payments? And for this, we will still use this inequality, which is also referred to as the payment differences sandwich, because here we have the payment differences and we're sandwiching it from the bottom and from the top by this formula. So now we'll move on with the proof of Meyerson's lemma. And what we'll now have to discuss is, if we have a monotone allocation rule, how do we find a truthful mechanism out of this? How can we set the payments? Why is the formula from the theorem giving us actually truthful payments? And to this end, we will simplify our life a bit, because we will only consider piecewise constant functions. So what might this look like? This now might look like this. We'll have, just like we saw this in the case of a single item auction, we might have a function which looks kind of like this. And again, what are we drawing here? This is z, and this is fi of z, comma b minus I. And what if we don't have such a function? We can actually do exactly the same things that we will be doing now. The only thing that gets different is that you want to approximate your function by such a piecewise constant function. You can always do this within any margin of error that you say. So just take any epsilon and then approximate your function to look like this way, and then go through the entire argument. And as you see, this has to hold for every epsilon. Then in the limit for epsilon going to 0, you'll get the exact same statement. But I'm not doing this here because I think this takes away the focus from the main part, namely understanding why these things are happening. What is now the thing that we want to show? Our proposition is let's consider any truthful single parameter mechanism and suppose that fi is monotone and piecewise constant on intervals zj, zj plus 1. So the first interval starts at 0, then the next starts at z1, and so on. And now what we're showing is that if when I'm bidding nothing, then I'm paying nothing, then we can now infer what the payment for any bid B has to be like. Because what we're doing here is we're summing up over all zj's, which are the endpoints of the intervals that are at most bi, and then we get zj times fi of zj, b minus I minus fi of zj minus 1, comma b minus I. Okay. Let's maybe, before we start with the proof, let's again look at our picture here. So what is now our notation? Our notation will be, this will be Z0, this will be Z1, this will be Z2, Z3, Z4, and so on. And what is it that now this function here is adding up? We are now taking any bj, bi, and now we are taking the sum over all zj, which are no larger than bi, and then we always multiply the respective zj by the increase of f. So we'll have this with j being 1, and for j being 1, we now multiply zj by the increase at z1, so this will be exactly this much. And then what we're doing next is we're also taking this for z2, so we'll have this area also being added up. So this formula down here, this corresponds to the area above the curve of the allocation function. Good. Let's now prove this. The first thing is, let's just consider any bi. And this bi will be in some of these intervals zj to zj plus 1. What do we now know about the payments? We know that the payment differences sandwich has to hold. And here we could now set y to bi and z to zj. And what are we getting from this? What will happen? Let's maybe go back to our picture. We have bi, and then we're comparing this to zj, so in this case z2. How does f change in between? F does not change at all in between. And what does this mean? If the f value for both y and z is the same, then the difference of the payments has to be 0, because this thing here will be 0 and this will be 0, so the difference of the payments has to be 0. So because fi of z, b minus I is equal to fi of y, b minus I, we'll have that also pi of z, b minus I is equal to pi of y, b minus I. So this means that pi is constant also wherever f is constant. And this would be the interval zj to zj plus 1. Next, let's consider any zj. If epsilon greater than 0 is small enough, then we'll have that fi of zj minus epsilon, comma b minus I, will be equal to fi of zj minus 1, comma b minus I. What does that mean? Let's go back to our picture. We are now considering any of these breakpoints, and this function is so that we'll fall down for any small epsilon. We'll always fall down to the next smaller interval. This is now stated here in just a fancy way. And what does this now mean? This now means that I'm paying, when I bid epsilon less, I'm paying as much as I'm paying when I bid zj minus 1. And also, what else do we have? We could now also compare zj minus epsilon and zj, and then what the payment differences sandwich will give us is the following. So set one of them to be zj minus epsilon. Then, let me just write this out here. This is just what comes out of this when you plug in this into the payment differences sandwich. So this is now comparing the points zj and zj minus epsilon via the payment differences sandwich using that, okay, fi of zj minus epsilon is exactly fi at zj minus 1, and also pi at zj minus epsilon is equal to pi at zj minus 1. Good. Now this is what we're getting out of this. And this has to hold for all epsilon which are small enough. So if we now take epsilon, the limit of epsilon to 0, this will still hold for every epsilon that is greater than 0. And once we reach the limit, we see, okay, this here will become the same thing as this. And this means that this thing in the middle of our sandwich has to be equal to what we're getting on both sides. This is exactly what I learned as the sandwich theorem a long time ago in my calculus class. And what does this now mean? This now means that the difference between the payment when we're bidding Zj and Zj minus 1 is exactly this. And now we're already there, because here this is nothing but adding up these differences. So how could we do this? For any bi that is somewhere in some zi, zi plus 1, what is it that we're getting? Let's rather call this zj prime. We will now be getting that pi of bi comma b minus I, this is equal to pi of zj prime comma b minus I. And this we can now write out as the sum of all these differences. So we will take the sum of all j from 1 to j prime, pi of zj comma b minus I minus pi of zj minus 1 comma b minus I. And then there is the last term that we're subtracting here will be zj zj minus 1 for j being 1. So let's add this again. So this will be the term for z0. But this we assumed is 0, and for these we just get the exact formula that we derived there. And this proves exactly our proposition. So we've now shown this proposition. What does this proposition actually say? If we have a truthful mechanism and we already know that then this function f will be monotone, and then the payment rule will have to look like this. So what is still missing? How does this payment rule actually compare to the one that we have in our theorem statement? That's the first thing that we will be doing now. And then afterwards we also, of course, have to ask, what if I now go the other way around? If I just have a monotone allocation function, and if I then take whatever payment rule this theorem tells me to take, will I get a truthful mechanism? Yes or no? But before, let's understand this payment formula here a bit better. What will this look like? Well, we now have pi of bi comma b minus I. This is equal to pi of zk comma b minus I. If we say bi is in the interval between zk and zk plus 1. So this we can now write down as given by our formula. And how can we now write this in a different way? Well, observe that each zj actually appears twice in here. It appears once here in the positive part and then also in this part that is subtracted. So what we might also do is we might split up these sums and how can we now recombine these? Well, we'll get that this is zk times fi of zk comma b minus I. And then, what else are we getting? We'll get and this is maybe now a weird way to write this, but it is exactly what we're up for. Because now these things combine in a really nice way. Now we have this is zk times f of zk minus the sum from 1 through k zj minus zj minus 1 times fi of zj minus 1 comma b minus I. And this is equal to the integral statement in the lemma statement. Good. So all that is now remaining is let's show that a mechanism which is built from a monotone allocation rule combined with the payment rule from the theorem statement, that this will always give us a truthful mechanism. So take any monotone allocation rule and let let pi of bi comma b minus I be equal to what we were stating in the theorem. This was bi times fi of bi comma b minus I minus the integral from 0 to bi fi of ti comma b minus I dt. And what we now claim is that f comma p is truthful. Why is that? First thing that we observe is that ui of b comma vi, so what will be my utility if I bid b bi, the others bid b minus I, and my value is vi, then this will be vi times fi of bi comma b minus I minus pi of bi comma b minus I. And now, if we combine this, then what we're seeing here is that this is vi minus bi times fi of bi comma b minus I plus this integral. And what can happen now? Let's first consider this in our example from before. So as you see here, we are this area above the curve, this is exactly this expression here. So this is the payment that we're setting. Now what will be my utility? This now depends on whether I bid truthfully or not. Let's first say that this vi is equal to this bi. Then this here will be 0, and my utility will be exactly this integral. So let's try to draw this here. So this might be now equal to my bi. So if I bid truthfully, then my utility will be exactly this much. What will now happen if I bid less? If I bid less than my true value, then I'm losing a bit. Because then, for example, if I bid only this much here, then, okay, I'm paying less, but I'm also getting less. Then my utility will only be and this is not super easy to see here, then my utility will only be this much. Why that? Because we're getting the area below the curve up to bi, and then vi minus bi times the height of the curve. But what you see is that we're losing this bit up here. So this is why you don't want to underbid. Let's now do the same kind of a comparison where we are overbidding. Now, my utility is how much? It is actually, first of all, we would say that this integral here, this would be like all of this. But then what we're losing again, what this will be like, this first term, this will now be negative. And what we're missing out here is exactly this piece, because all of this is then, this entire rectangle is then subtracted. So also here, then the overall area will be smaller than just this green area. Good. This is how you can interpret this visually. We can also do this now just very algebraically. If we now say if bi is at most vi, then ui of b comma vi minus ui of vi comma b minus I comma vi, this will be, and then we just use the formula vi minus bi times fi of b plus the integral and then we subtract the utility that you're getting when you're bidding truthfully, which is just the integral from 0 to vi of fi of t comma b minus I dt. And what we're now seeing is that here, this is of course the integral from bi to vi of fi of t comma b minus I dt. And how much is this? This will be this is minus that, because here we're integrating for longer than here. And now the point is this here, this is more than this. So this will be non-positive. Same thing for if bi is at least vi, then ui of b comma vi minus ui of vi comma b minus I comma vi. Then, well, first the same inequalities, the same equality holds, of course. And now this much here will be the integral from vi to bi fi of t comma b minus I. But now the thing is, again, the same as before. This here cannot make up for the value that is lost, because this will be at most, if we take the bi minus vi times the maximum value that we ever see in this interval, which is bi, and then we'll also get that this is non-positive. Great, so this way we have now shown Meyerson's lemma. What did we show? We showed that an allocation rule is implementable if and only if it is monotone. And we also showed that if it is monotone, then there has to be unique payment rules such that it becomes truthful. Once again, when did we show what? The first thing that we showed was an allocation rule has to be monotone for it to be implementable. And then we also showed that for the mechanism Fp to be truthful, it has to follow, the payments have to follow this formula. And then the last thing that we did was, if now the allocation rule is monotone, then combining it with these payments will always give us a truthful mechanism. What were the main ideas for these necessary conditions for a mechanism to be truthful? We used this payment differences sandwich, where we said, okay, my actual value could be y and I'm bidding z, but bidding y should be better. Or my actual value could be z, but bidding y shouldn't be better either. But the mechanism cannot actually distinguish between whether my real value is currently y or z. And has to do the same thing regardless of what my actual value is. It can only make a difference on depending on what I'm bidding. This is where the payment differences sandwich was coming from, and this is usually very helpful if you want to understand in any way what a truthful mechanism has to look like, so if you want to derive any necessary properties. And then, okay, showing that this will result in a truthful mechanism, that's actually not super complicated, because you just have to compare what could I bid instead. And whatever I bid instead will give me no larger utility. Now, let's once again see what this means in the context of our examples from last time. Let's now discuss how we can come to truthful mechanisms from allocation rules via this formula. What does this even mean? And let's start with a single item auction first. In this single item auction, what will our allocation rule look like? We could, for example, take the allocation rule, or we should take the allocation rule in which the bidder with the maximum bid wins. What will the curve look like? We've seen this before. This will be 1 up to some point, 0 up to some point, and then it will be 1. By the way, this is bi, this is fi of bi, comma b minus I. And this point here, that's the maximum of all j, of all bj, where j isn't equal to I. So this is the maximum bid except for I's bid. Now, what will this formula tell us? How much will I have to pay? So this, of course, depends on how much I'm bidding. Say I'm bidding this much. Then, okay, I'm not getting anything, and what will this be like? Fi of bi will be 0, and also this integral, this will also be 0 because we're just taking the integral for only within here. Good. So I'm not paying anything, I'm not getting anything. Cool. Now what if I'm bidding this much? How much will I be paying then? How much is this? Now bi times fi of bi comma b minus I, this will be quite a bit, namely this is the entire area here. But from this we subtract something, namely the area below the curve. So this much I'm subtracting. So what is remaining will be this other area. So then pi of bi comma b minus I will be the maximum other bid if I wins with bi against b minus I. And this, I hope, looks familiar, because this is exactly the second price auction. And what Meyerson's lemma tells us is that unless we're giving the item somebody else than the bidder who bid most, this is the only truthful mechanism. You might now discuss how could we give this to anybody else except for and still get a monotone allocation rule? Yeah, well, for example, you could give it always to the youngest bidder, or you could sometimes keep it for yourself. That would be certainly different mechanisms which would also be implementable truthfully. But if you always give the item to the highest bidder, then the only truthful mechanism that is possible is the second price auction. Let's see another example, which is the sponsored search auction. So here now things will look a little more complicated because we now have multiple steps. If you what was this like? Well, we have the different ad slots, and those have different click-through rates. So this might be the best slot will give us a click-through rate of alpha 1, the second best will give us a click-through rate of alpha 2, the third best of alpha 3. So we'll have, in this case, k equals 3. Now, what I've already drawn here would be a monotone allocation rule. Namely, we always assign the slots by decreasing bid. So whoever bid most gets the top position, whoever bid second most gets the second highest position, and so on. And what will then, this will again result in a monotone function, which then looks like this. And what will the payments be like? Well, it is again the area above the curve. So let's see this also here. We would, for example, if I'm bidding this much here, then I'm getting the second slot, and how much am I paying? I should be paying this much. What would be the formula for this? We would now get that pi of bi comma b minus I is equal to the following. Take the sum over all slots of higher index, and now you ask, what is this? So this here, this is the j plus 1 highest bid, and the point is now, where are these points here? This is all defined without taking me into consideration. So this is the highest bid except for mine. This is the second highest bid except for mine. This is the third highest bid except for mine. And what will now happen if I, for example, I'm getting here, and then how much do I have to pay? I will have to pay this area times this point. And this is written down in this formula. This, I hope you remember, came up in our proof as an equivalent way of stating this formula. There's also a different way to interpret this formula, which we will be seeing sometime later, but not so far from now. Good. So also here there is a truthful mechanism. It has a unique payment rule, but interestingly enough, this is not what Google and all were doing, maybe because they didn't understand how one designed truthful mechanisms, or for some other reasons. Maybe they wanted to keep things simpler, because what they introduced instead was something that they called generalized second price, which feels similar to a second price auction for the setting, but where the payment rule is slightly different. And then, of course, this will not be a truthful mechanism, because, as we've shown, the only way we are getting a truthful mechanism is by exactly this payment rule in this setting. Unless, of course, we make the assignment in a different way. That's still possible. And this way you can, of course, always get also other truthful mechanisms. And in many cases, this will be actually trivial mechanisms. Good. So this is concluding our lecture for today. We've seen this characterization of truthfulness for single parameter settings. What we'll still have to discuss, how can we define such monotone allocation rules, which are good in any way? And then also what we'll have to discuss is, what can we do if we're not in a single parameter setting? Because then all of these nice things don't actually hold, and there is no such nice characterization. Good. So this is what we'll continue with next time. Please reach out to me if you have any questions. Stay safe and have a great day. Bye.